Welcome to the Deep Dive. We're here to unpack those big ideas and hopefully give you some real aha moments along the way. Today, we're tackling something that might sound a bit daunting, but it's actually super powerful and honestly pretty fascinating. Instantaneous change. I mean, think about it for a second. How do you actually describe something that's changing at one single exact moment in time? Like, what's the speed of your car right now? Not the average over the last hour, but right this instant. Or, how steep is that roller coaster track right at the very top, that one specific point? It almost sounds like a contradiction, doesn't it? Change usually means over time, but instantaneous means, well, no time at all.
That's a fantastic question. It really cuts to the core of what calculus lets us achieve. To pin down these moments of change, mathematicians came up with this key tool, the derivative. Now, for you, just starting out in calculus, you've probably heard about derivatives using limits. That's the standard approach, absolutely. But today, we're going to look at it through a slightly different lens, using infinitesimals. It's a really intuitive way, I think, to grasp that idea of infinitely close. So our goal today is twofold. First, to give you a solid feel for what the derivative is, using this perspective. And second, maybe even more importantly, to share some powerful learning strategies, not just for derivatives, but for tackling, well, any complex subject you run into.
Okay, let's get into it. The derivative. You said it's how we find the slope at a point on a curve, which is, like you said, totally different from finding the average slope between 2 points far apart, like we do in algebra with straight lines.
Exactly. So the formal starting point is something called the difference quotient. Imagine you've got a curve. Now, picture 2 points on that curve that are incredibly, unbelievably close together. Think about zooming in and in on your graph. So close that these 2 points are almost touching, like side-by-side pixels on a super high-res screen. That tiny, tiny distance between their x values. That's what we call delta x.
Okay, delta s.
Right, delta x. And it's a non-zero infinitesimal. That means it's incredibly small, smaller than any positive real number you can name, but, and this is key, it's still not zero.
Got it. So not zero, but closer to zero than anything we normally think of. So we're dealing with 2 points, basically neighbors at an infinitesimal level. The difference quotient, then, that's the change in the y value.
Which is f of I plus delta x minus f of a.
Right, that change,
Yeah.
divided by that tiny change in x.
Exactly, over delta x.
So it gives us the slope of a line, but a special line, hyperbola line, connecting these two infinitesimally close points. It's not quite the tangent line slope yet, but it's super close.
Super close is right. And here's where the idea of the shadow comes in. That difference quotient, that slope of the hyperline, is a hyperreal number. It includes that infinitesimal bit. To get the precise real-world slope at the single point A, we take its shadow. The derivative, which we write as f prime of x, is defined as the shadow of that difference quotient.
The shadow. Okay, I like that. It's like you're getting rid of the infinitesimal fuzziness, leaving just the clean, real number that represents the slope.
That's a great way to put it. It's the real value that the slope is infinitesimally close to. It bridges that gap you mentioned, the contradiction of change at an instant.
Yeah, that shadow idea really clicks. It's like focusing a blurry photo. Suddenly you see the exact state at that one moment. Okay, so let's make it concrete. A straight line, easy, slope's the same everywhere, but a curve, maybe like y equals by 2, it's always getting steeper or shallower, right? The steepness changes.
Precisely. The derivative gives us that exact rate of change at any point x on that curve. For y equals on that curve, for y equals by 2, the derivative f prime of x actually turns out to be 2x.
Oh, interesting.
So if x is 1, the slope is 21, which is 2. If x is 5, the slope is 25, which is 10.
So the derivative itself is a function that tells you the instantaneous slope anywhere on the original curve.
You got it. It gives you a formula for the steepness at any point x.
It's still kind of amazing how a single point can have a rate of change. It feels like it shouldn't, but the math makes it work. Okay, so we have the core idea, but knowing what it is and actually mastering it when you're facing homework or an exam, those are different things. You mentioned learning strategies. Calculus can feel like this dense forest, right?
It definitely can at first. But here's the good news. Your brain already has the equipment you need to navigate it. It's less about innate talent and much more about how you use your brain.
Okay, I'm listening. How do we use our brains better?
Well, one key idea is understanding the difference between focused thinking and diffuse thinking. You can imagine focused thinking like a pinball machine where the bumpers, the neural pathways, are really close together. It's great for working through steps you already know, like doing a calculation or following a familiar procedure for a derivative. Your thoughts bounce along established paths. But if you get stuck, Sometimes your thoughts just keep hitting the same few bumpers, right? You're stuck in a rut.
Yeah, I know that feeling, going over the same wrong step again and again.
Exactly. Now, contrast that with diffuse mode. In that pinball machine, the bumpers are spaced way out. This lets your thoughts travel much further, make connections between different ideas, see the bigger picture.
Huh.
Think of focus mode as a flashlight, a tight, intense beam. Diffuse mode is more like a lantern spreading a softer light over a wider area. You absolutely need both.
So when you're starting a derivative problem, you use the flashlight, the focused mode. But if you hit a wall...
That's your cue. It might mean you're experiencing something called the Einstellung effect, basically, being mentally blocked, fixated on an approach that isn't working.
Einstellung effect.
Yeah. That's when you need to switch to the lantern, the diffuse mode. Take a break, go for a walk, listen to music, do something else entirely. It sounds counterintuitive, but letting go allows your brain to work on the problem quietly in the background. It makes those surprising connections. Think of famous examples like Magnus Carlsen looking away from the chessboard, or Edison using naps for insights.
That makes a lot of sense.
Yeah.
Don't just keep banging your head against the wall. Let the background processes kick in.
Yeah.
Okay, so diffuse mode helps with breakthroughs, but how do we make those breakthroughs, or just the regular steps, stick, make them more automatic? You mentioned chunking.
Yes, chunking. This is so fundamental. It's about grouping separate bits of information together into a single conceptual unit bound by meaning. Think of it like creating a .zip file on your computer. You take a bunch of related stuff and compress it into one package.
Okay, like a mental shortcut.
Exactly. It makes your thinking way more efficient. Instead of juggling lots of little pieces, your brain just grabs the one chunk.
How does that apply to derivatives?
Well, think about the steps we talked about for finding a derivative from the definition. You expand f of x plus delta x minus f of x. Then you factor out the delta x. Then you cancel it. Then you take the shadow.
Right, those 4 steps.
Initially, each one takes conscious effort. But with practice, those 4 steps can become one smooth, connected chunk. You just find the derivative chunk without thinking intensely about each microstep.
So how do we build those solid chunks? Just keep doing problems.
Doing problems helps, but how you do them matters. Simply rereading your notes or examples, that often creates an illusion of competence. It feels familiar, but the knowledge isn't really yours yet.
Uh-oh. I think I do that sometimes.
We all do. The much more effective way is retrieval practice. Close the book. Try to recall the steps from memory. Try to solve a problem without looking at the solution first. It's harder, yes, but that effort is what actually builds and strengthens the neural connections. It's like letting mortar dry when building a brick wall. Rereading is like constantly poking the wet mortar. Retrieval lets it set.
Active recall, not just passive rereading. Got it. That's a really useful distinction.
It really is. Now, something that totally undermines both chunking and diffuse thinking is procrastination.
Yes, the old enemy.
It's not just about losing time, though that's bad enough. When you procrastinate, you rob your brain of the time it needs for that diffuse mode to work its magic. That background processing, that simmering of ideas, it doesn't happen on command. It needs time. Putting things off means you don't give your brain that essential incubation period.
That's a great point. The diffuse mode needs lead time, which procrastination steals. So, okay, we know procrastination is bad. How do we fight it, especially when a problem looks really hard?
It's tough, but one really practical, concrete method is the Pomodoro technique. Have you heard of it?
Vaguely. Something about tomatoes.
Yeah, the timer often looked like a tomato. The idea is simple. Set a timer for, say, 25 minutes. For those 25 minutes, you focus only on your calculus work. No phone, no email, just focus. Then, when the timer goes off, you take a short break, maybe 5 minutes, do something enjoyable, reward yourself a little, then repeat.
So short bursts of focus, then a reward.
Exactly. The key is you're not trying to finish the entire assignment in one go. You're just committing to starting and working for 25 minutes. That makes it much less daunting. It helps overcome that initial hurdle, gets you into the task, and those short breaks actually allow a bit of diffuse thinking to happen naturally.
I like that, breaking it down, focusing on the process, not the huge end goal. Okay, one more strategy area. Embrace struggle. You mentioned getting stuck isn't failure.
Absolutely not. Getting stuck is normal. It's often that Einstellung effect. Again, you're stuck in a focused mode rut. But feeling confused or stuck is actually a signpost. It shows you exactly where you need to focus your learning efforts.
So don't run away from the confusion.
Lean into it. As one learning expert said, just being able to clearly state your question, to articulate why you're confused is like 80% of the battle. Grappling with confusion, really wrestling with it, that's where the deep learning happens. Switching modes between focused effort and diffuse breaks is often how you get those breakthroughs.
And to make practice more effective, especially with struggle, you also recommend interleaving.
Yes. Interleaving is crucial. Don't just drill 20 problems of the exact same type from section 3.1.
Right, mix it up.
Mix it up. Do a problem from 3.1, then one from 2.5, then maybe one from 3.2. This feels harder in the short term because you have to keep figuring out which technique applies, but that's exactly the point. It prevents you from just blindly applying one method you've overlearned. It builds mental flexibility.
Like a carpenter needing to know when to use a hammer versus a screwdriver, not just being good with a hammer.
Perfect analogy. You learn to recognize the type of problem and select the right tool.
These strategies are really helpful. It's about working with your brain, not just forcing information in.
Exactly. And speaking of understanding deeply, it's also really important to know the limits of a concept, like where don't derivatives exist?
Good question. When does this idea of instantaneous slope break down?
Understanding the boundaries is key. These failure cases are incredibly instructive. They force you to think harder about what the derivative actually means. There are basically four main situations where the slope of a function f might not exist at a point x less a. First, simplest case. The function f of a isn't even defined at that point.
Like 1 over x at x equals 0.
Exactly. Or your example 1 over x plus 2 at x equals 2. If the point isn't there, you can't talk about its slope.
Makes sense. What's number 2?
Second, the difference quotient itself might be undefined. This can happen if f of a plus delta x is undefined for some infinitesimals delta x. Think about f of x, x dash 3, right at x is negative. Even infinitesimally negative, then a plus delta x is less than 3.
And you can't take the square root of a negative number in the reals.
Right. So you can't even form the difference quotient if you approach from the left. No second point means no slope calculation.
Got it. Can't connect the dots if one dot isn't really there for the function. Okay, third,
the difference quotient might become unlimited, basically go towards infinity, for infinitesimals delta x. The classic example is f of x at x equals 0. If you work out the difference quotient, it involves 1 over delta x to the 2/3 power.
And as delta x gets tiny, dividing by it makes the result huge.
Infinitely huge, in fact. Graphically, this looks like a vertical tangent line right at x0. The curve goes straight up and down for an instant. The slope is infinite, so we say the derivative doesn't exist as a real number.
Like a vertical cliff face, infinite slope. Okay, and last case.
The fourth case is when the difference quotient has different shadows depending on which direction delta x approaches 0 from. The absolute value function, k of xx, is the perfect example, right at x equals 0.
A sharp point.
Exactly. If delta x is positive, approaching from the right, the slope, the shadow, is 1. But if delta x is negative, approaching from the left, the slope, the shadow, is -1.
Because the slopes are different coming from each side.
There's no single unique value for the derivative at that point. The shadow depends on how you look at it. So no derivative exists there.
That sharp corner means no single tangent line, no single slope value. Makes perfect sense.
And again, these aren't just exceptions to memorize. Thinking about why the derivative fails in these cases, undefined point, undefined neighbor, infinite slope, different slopes from different sides, that deepens your understanding of what it means for a derivative to exist. It has to be smooth and well-defined at that infinitesimal level.
That's a great way to frame it. These aren't failures, they're insights into the conditions needed for a derivative. So wrapping up this deep dive then, the message seems to be that getting good at calculus, mastering derivatives, it's not about cramming hundreds of examples.
Not primarily, no. It's much more about consistently practicing these learning strategies we've talked about. Use focused bursts of work, like the Pomodoro. Intentionally take breaks to let your diffuse mode kick in. Practice active retrieval test yourself. Explain concepts out loud, work problems from memory, build those chunks, and really truly learn to embrace the struggle. See confusion not as a stop sign, but as a signal that you're on the verge of understanding something new. Your brain literally grows from that effort.
You already have the tools, this amazing brain. It's about learning how to use those tools effectively. Learning calculus is learning how to learn.
Beautifully put. And maybe a final thought for you to take away, that feeling of confusion. It's not failure, it's a signpost pointing directly at your next learning opportunity. So after this deep dive, what confusion are you going to lean into next? What are you curious to explore further?